Okay, so let's start with Lewis acids and Lewis bases. That'll get us into everything, I think. Okay, so if something is a Lewis acid, what does it need? There's basically three different scenarios where something can be a Lewis acid. Do we remember what they were? So one is basically an empty, low energy orbital. So something like BF3, something like a carbocation. So these got empty orbitals. In these two cases, it's p orbitals. The other two, the other things which have empty low-lying orbitals are metal cations. So this could be things like lithium plus. This could be transition metals. So zinc dichloride, titanium, something like this. So this is less, we don't see this very often. This is less common. At least less common this term. The other third thing is a polar bond to hydrogen. So we could have anything which is bonded to, the most common example would be a hydroxyl group. So polar bond to H. So if some base comes along and grabs this, the Lewis acid has effectively accepted the lone pair which is in this bond. So Lewis acids are basically, they have these three characteristics. And so this last one this is basically the same as a Bronsted acid. So to be a Lewis base, this is a lot easier. It's basically something which has an electron pair. It can donate. And so species with electron pairs, the most oxygen containing functional groups, nitrogen containing functional groups, sulfur containing functional groups. These are basically all. So, or even things like if you have a carbonyl, it can technically donate a lone pair to grab a proton, for example. And it would be behaving as a Lewis base. So those are the common definitions of these things. So this becomes important, I suppose, in substitution reactions because we've got, there's a number of examples where the nucleophile is essentially a Lewis base, right? Because it's got a lone pair which it can attack. It can use to attack something, which either a proton or a nucleus. And so it's using that lone pair to donate. So this plays a role because the Lewis bases are the nucleophiles or the bases in substitution and elimination reactions. Now, let's erase something. Let's erase this stuff over here. Let's see here. Okay, let's do. Okay, so if you've got a let's pretend that we've got a structure like this. So we've got THF and it is dissolved in some water and it's in the presence of HI. If we were to, and this, a derivative of this question is on the old midterm. The first part of this question, though, is a simple Bronsted-Lowry acid-base question. We have got a strong acid, Bronsted acid, and we've got a Lewis base, which means that this can be a Bronsted base too, right? So the first step is that these electrons are just going to come and grab this proton, and our iodide is going to leave. So we probably even might have had this question on the midterm right at the very start of the year. And the product, the first step of the product for this is actually this. We would have protonated our oxygen, and we've got iodine, which is left, or iodide, which is left. These two structures can actually do a second reaction based upon what we know from substitution reactions. Because we now have a good nucleophile, and we now have a structure that has a good leaving group associated with it. Because remember, like water itself was a good, hydroxide's a terrible leaving group, bad, but water's actually a pretty good one, because when it leaves, it's leaving as a neutral molecule. So in this case, this would further undergo basically it could undergo an SN2 reaction. Attacking this carbon here, and then you would end up with our product. There's an extra electron there. So Yeah, so at the very start of the year, these two were a perfect answer to the thing. But actually, there's a second step. That was only technically the first step, the way that this reaction could proceed. So if we go back to one of the things that we're looking at a reaction scheme, sometimes the first thing we should look for is there an acidic proton that we can grab, as opposed to if you think of E2 and E1 elimination reactions, let's do an E2 here. So our base is coming along and it's grabbing this proton and that's leaving to form our alkene. This proton is actually attached to a carbon atom, right? So it's, when we were going through what's the most acidic proton in a molecule, we wouldn't have chosen these protons because they're attached to carbon. Usually we'd be picking protons that are attached to, say, oxygen or sulfur or whatever it happens to be. So don't lose sight on the fact that some reactions are just going to be acid-base reactions where you're deprotonating just an acidic proton. And that's sort of a hint for one of the questions that was asked in chat. So sometimes acid-base reactions are, don't get lost looking for stuff when the real reaction is just an acid-base reaction of now. So right, Lewis bases will have electron pairs they can donate. Lewis acids will have a polar bond to H, or an empty low energy orbital, either a d orbital for transition metals, an s orbital for like magnesium and lithium, or a p orbital in the case of carbocations and like boron complexes. Now I got a question here about with two potential leaving groups. Clear. Okay, so let's pretend that we've got this and I don't know, this. And we are using some nucleophile. And this is in DMSO. Let's do another example here. Okay, so in this first example, what's a better leaving group? Hydroxide or iodide? Right, so hydroxide is one of those things which is a terrible leaving group, right? So this is terrible. NH2 would be terrible. Even F minus isn't very good. It's terrible. So these are all awful. And then there's basically things that are better than that. If we're comparing things that are negatively charged, as you go down the periodic table, they get progressively better. So this is better, iodide would be better. And then the sulfonates is equally good as iodide. So the triflate would be the best one. So the OT, which is approximately equal to OTOS. Triflate's the best one. Okay, so that means that, so SH minus, this can only be a nucleophile. If we try to do this reaction here, if we try to do this and make this product, what's wrong with this? If we try to do an acid-base reaction with this, what's wrong with this? That little chat thing. Okay, so let's do an analysis of, okay, and we'll just do it with something simple here. So this is an acid-base reaction, right? Which direction does this equilibrium lie? What charge is more stable? Negative charge on a sulfur or negative charge on an oxygen? Right, the negative charge on the sulfur is the more stable. And why is this more stable? It is stabilized in right, stabilized in a larger orbital, right. So this reaction itself would lay on this side. This would go in this direction. So this sulfur is, if we go back to this acid base, if we go back to this reaction here, this S minus is not going to deprotonate this hydroxide because in fact it should be going the other direction. This negative charge is stabilized in this large sulfur orbital, which is one of the reasons why SH minus is never going to be a base. It's always going to be a nucleophile. So then if we're looking at our substrate where it could attack, we've got one group which is a terrible leaving group, which would in fact generate a stronger base, this one here. Hydroxide would be a strong base, right? So remember, the best leaving groups are extremely weak bases. So that's why hydroxide is a terrible leaving group, which means that the only option left is the iodide. So we are only going to do the substitution on this one side. So our product will be the OH is going to stay. SH. And our leaving group, the iodide, this negative charge is also stabilized in this great big orbital for iodine. So it's quite happy being a good leaving group. So this is one example where you're basically, you can compare along the continuum of what's a good leaving group for which is a bad leaving group. And this comparison is good because both of the leaving groups are on primary carbons. Now, in fact, this is such a terrible leaving group, it doesn't matter which carbon it's on, it's not going to leave. But here's an example where we've got the same leaving group, which would be iodide, on two different carbons. And so if we had one molecule of this and one molecule of this, the sulfur is only going to react at one place. Which one would it react at? Would it react at the secondary one or would it react at the primary one? Okay, primary, and why would it react at the primary one and not the secondary one? That's correct. Exactly. Less steric hindrance, it's easier to access. So we've set this up so it's going to be should be an SN2 type reaction. So this would come and attack here, and that would leave. So we would form this SH. Now I suppose I could get tricky and do this. In water. Or even I could do this. Let's do this one instead. Okay, now where should we expect the sulfur to attack in this case? Now we've got a tertiary, and now we've got a primary. So what I've done is I've done two things. I've reduced the nucleophilicity, so it's no longer got a negative charge, and I've made the solvent protic. Protic solvents favor what kind of reactions? If we're talking about substitution. So protic solvents favor SN1, that's right. And if I reduce the nucleophilicity of this, so it's no longer got a negative charge, so this is a weaker nucleophile, it's still only a nucleophile, but it's just weaker. I'm trying to promote an SN1 reaction because protic solvents favor SN1, and having a weak nucleophile is going to help promote that as well, because the nucleophile isn't part of the rate determining step. So in this case, with these conditions, we would expect this iodide to leave first, because we would form a more stable carbocation. And then the sulfur can come in and attack. And then we would end up doing the substitution on the other carbon. So when you're, if the substrate's got two different leaving groups, one of the things that, and these types of reactions, these questions are better questions when we're debating between substitution SN1 and SN2. The thing you want to check for is to see if, okay, which type of reaction is being promoted here? Is this supposed to be an SN2 or is this supposed to be an SN1? So remember, SN2 will be aprotic solvents, SN1 will be protic solvents. SN2 will have really good nucleophiles. SN1 will have species that are really best at being nucleophiles, but they don't necessarily have to be they don't have to be super nucleophiles, right? They just have to be something which can only be a nucleophile. That would be the best way to promote this. So sulfur is a really good example. And then you can see which type of carbon it's on, the leaving group, and make that determination this way. So for SN2, they're the fastest on primary, and they're slower on secondary. And on tertiary, they don't work at all. But for SN1, tertiary is the fastest, followed by secondary, and then they don't work at all on primary. So there might have been a couple questions on the assignment similar to that too. So there's two ways to go about asking these sort of questions. One is having the two types of leaving groups on a similar carbon, like primary versus primary, or having the same leaving group on different types of carbons and determining what type of reaction it's going to be. Okay, let's clear this for us. Okay, so yeah, the product for this reaction. So let's move this over here. So we would have the first step would be this. You would have sulfur, which is protonated. Now this isn't gonna last long in this form, because this is these protons on the sulfur would be super acidic. So water would just come along and grab one of those. And so you would end up with the SH on the, so it's not going to be SH2 because that's got a formal charge of plus, and that's going to get deprotonated really quickly. And it's the same thing if we were doing this reaction within water. So it was just water was the nucleophile and water was the solvent. Our final product would be the hydroxyl group there, the alcohol, not H2 plus, because that's very acidic. So this step here would be very fast. Okay, let's clear all this. me think. No, I don't. That's this. Trying to think of a good question to ask. Okay, 1 second here. Let me find something here. Just trying to dig up that old test here. Okay, yes, we'll do that in okay, so okay, so a question was asked about filling in the reactants. How do we choose what we're going to do, that type of thing. So here's an example. Let's try some of these. This would be, let's try some of these. So right. Okay, so I've got 3 different reactions here. Call this one A, B, and C. And how do we go about figuring out what we want to do in each case? That's a good question. So I guess what's the first question we want to ask ourselves in a situation like this? Right. Like, so the first question we could ask ourselves is, what type of reaction do I need to do? Okay, so here we've got, and in this case, it's a more, it's not super specific in the sense of E1 versus E2 or SN1 versus SN2. It's just, do I need to do, the first question is it an elimination reaction or is it a substitution reaction? I would start with the very broad basics, like those two global types of reactions. What do I need to do? Is it an elimination reaction or is it a substitution reaction? So in the case of A, what are we doing? Right, we are starting with an alkyl halide and we are ending with an alkene. So this means that we are doing an elimination reaction, And so A is an elimination reaction, B is an elimination reaction, and C is a, we started with a bromine and we're ending with a hydroxyl group. So C is a substitution reaction. Okay, so now substitution reactions. Let's do this. Let's do the substitution reaction first. Okay, so once we've determined that we're doing a substitution reaction, then what's the next question we're going to ask ourselves? Right. Is it an SN1 or is it an SN2? Okay, and the best way to figure this out is going to be doing what? What are we going to look at to determine if it's going to be an SN1 or an SN2? Okay, so we can look at, okay, the first thing I would look at is the type of alkyl halide we've got. So this bromide we're starting with has got 1, 2, 3 substituents. So it is a tertiary. So if it's a tertiary alkyl halide, it can only be one type of substitution reaction, right? So if it's tertiary, it can only be SN1. If it was a primary, it can only be SN2. So tertiary could only be SN1, primary could only be SN2. Now, if it was a secondary, then we would need to, like, okay, let's pretend let's have this. And our product was this. Then, or another possibility would be that, right? So if it's secondary, where both primary and secondary can take place, then we need to look at what's happened to the chiral center. If the chiral center has been reversed, then this would be SN2. And if it had been racemized, then it would have to be SN1. But you'd only have to get into the nitty-gritty about this type of analysis if it's a secondary alkyl halide, because if it's a primary, it's got to be SN2, and if it's a tertiary, it's got to be SN1. So in this case here, we are, because it's tertiary, we have to be doing an SN1 reaction. Okay, so if it's an SN1 reaction, what type of solvent do we use in SN1 reactions? We need protic solvents, right? Polar protic solvents. Okay, and the rate equation for a SN1 reaction is some rate constant times by the concentration of Rx. So there is no nucleophile in this rate equation. So we're going to want to use a weak nucleophile to do this reaction. So our solvent needs to be protic, and the group we're attaching is a hydroxyl group. So what would be a good solvent to use in that case? Water, right. It's a nice polar protic solvent, and it greatly resembles the substituent, which is actually doing the substitution reaction. Okay, now what do we want to use as the nucleophile in this case? Water. Right, we want to use water. Why don't we want to use hydroxide? Why is hydroxide a bad choice? Yes, it's a strong nucleophile, but it's also a strong base, right? So if we use something which has got a negative charge, this could behave as a base, and we don't want this to do any side products, side reactions like elimination reactions. So if a really good choice for in SN1 reactions is to use the solvent's actually the nucleophile itself. So what we would call a solvolysis reaction. So if this group here, let me erase something. Let's erase this H, and let's put an Me here. So instead of being replaced with the OH, it's now being replaced with the OMe. The only thing we would change in our setup here is that, okay, we wouldn't use water as our solvent, and we wouldn't use water as our nucleophile. We would change this to match. So methanol would be the solvent because it's still a polar protic solvent, and it would also be the nucleophile. So we still have an oxygen nucleophile which could attack that carbocation. And the intermediate right before the final product would be formed would be this. And methanol is just going to come along, and it's going to grab that proton super quick, and that's going to be your final product, will be that. So remember, it's super easy to remove little protons. So if this was like a methyl group, if this was a methanol, like methyl or a ethyl, all we would do is change that over here, and we're not going to go wrong. So we've chosen a polar protic solvent, which is going to favor SN1, and we've chosen a really weak nucleophile that isn't going to do some crazy side reaction, which if you ever use something with a negative charge, it's really going to promote an elimination reaction. So we want to avoid these types of things at all costs for doing a substitution reaction. So that's how I would basically tackle. Let me move this chat over here. That's basically how I would tackle one of these questions. The first thing I would ask is, am I doing an elimination or a substitution? Just the global, what is it? Then if it's a substitution, the next step would be look at the type of alkyl halide, or is it a tertiary? It has to be SN1. So choose things that will promote SN1. If it's primary, it has to be SN2. If it's secondary, then I would have had to have given you, where's my little drawing thing? I would have had to give you other details. Is the stereochemistry reversed, or is it racemized? I'd need to tell you that, or else if I didn't tell you that, then it's the question's starting to lose some of its meaning. So that would be the first thing I'd look for. Is it an elimination? Is it a substitution? If it's substitution, then look at the alkyl halide and figure out, is it SN1 or SN2? And then use solvents and nucleophiles that will promote those two things. Let me erase some of this other stuff here. Now, the other two reactions here are eliminations. Okay, so we're going to do a similar analysis with that. Sorry, before I move on to that, does that make sense? How we sort of figured those things out. Okay, now, if it's an elimination reaction, the point that we're gonna do is that, okay, so there's a clear difference between this product here and this product over here, right? One of them has, so once we've done, if it comes to elimination reaction, there's two, in this case, there's two constitutional isomers that have formed here. This is a tertiary alkyl halide. The difference between elimination reactions and substitution reactions is that E2 eliminations can take place on primary, secondary, and tertiary alkyl halides. They work equally well for all of them. So we can't do that same similar analysis of looking at the alkyl halide and trying to figure out, is this a substitution or SN1 or SN2? Because in most instances, we can use an E2 to get the products that we want. So in some ways that's a bit helpful. But when it comes to elimination reactions, there's really two types of products that we could form. One to form the more stable substituted, I guess we'll use that. And one to form the least substituted. Alkene. So this would be Hoffman's product, Hoffman, and this would be Zetyev's product. And so all we have to do here is change the type of base we're going to use. So E2 elimination reactions, if we're using oxygen-based bases, we are going to use protic solvents. So, and it's going to match what the nucleophile looks like. It's going to be the conjugate acid of them. So if we're using a like methoxide, which is a strong base, we are going to do this in methanol. If we are going to use tert butoxide, we are going to use this in tert butanol. And you can basically, these two could be used repeatedly to do what you want to do. So remember, the smaller bases, they form the more substituted product. Larger bases form the least substituted product. So for most alkyl halides, we can do an E2 elimination. And what I would look for is to see, what do I have, the more substituted alkene or do I have the least substituted alkene? If it's the least substituted alkene, I'm going to want to use a big bulky base, and tert butoxide is a perfect choice for that. And we want to use the corresponding conjugate acid as the solvent. So with methoxide, use methanol. With tert butoxide, use tert butanol. If you had ethoxide, sorry, use ethanol. If you had isopropanol, isopropoxide, I guess, use isopropanol as your solvent. Those, but you can get away with actually just using methoxide or tert butoxide as your basis for these cases. But because the E2 can be used in all of them, and the E2 elimination is fast, it makes more sense to set up an E2 elimination than an E1, because an E1 would take, in some instances, would take a long time, and you can't do it for a primary. So it wouldn't work. Why is this doing this? Oh, silly thing. It wouldn't work in this case. Like if it was trying to do an E1, it's almost unpractical. So all of the examples we're going to do, you can get away with using an E2. So let's see here. Okay, so over the next 2 minutes or 3 minutes or 4 minutes, think of some reagents that you would do for here and here while I go refill my coffee. And then post them in, you can discuss it as a group or whatever, and I'll be back in 2 seconds. And I will pause the recording. Okay, so do people have some answers? Let me see if I can. I have one, there's, okay, so it's, okay. 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 So, okay. Right now, what was I? So someone asked, how do we know if the counter ion, is it potassium or is it sodium? In most, like, it just so turns out that tert butoxide, negative, they sell it commercially with potassium as the counter ion, but things like methoxide, it's typically made, and sodium's the counter ion. Because what you can do is you can just take sodium metal and you can dissolve it in, say, methanol, and that's going to generate the methoxide, the sodium methoxide. But in the grand scheme of things, I would be less worried about those sort of things. You can usually put either there, and it's not, even you can sometimes put lithium there. Sorry, I gotta get rid of a cat here. Okay, let's see here. So any other answers besides the one that was sent to me? So in version A, are we making the more or least substituted alkene? Right, we are, so here's our leaving group. I'll put a little star on it. So remember, protons are being removed from either the carbons next door. I should go into the top hat where I can get some colors here. So the two possible products would have been this one, and the other one would have been this one. So we've got, for version A, we've got the more substituted alkene. And so to generate the more substituted alkene, you'd need a smaller base, right? So there's been a couple of people who have said this. And that would be correct. If we'd made the one here where the double bonds on the terminal end, then we would use the bulkier base. So tert butoxide in tert butanol. So how do we know which base to use? It depends upon, is it, if you're making the more or least substituted alkene. So for the least substituted, you want to use the bulky base. And for the more substituted, you want to use the small base. small. And two examples are for a small base, the methoxide and methanol; for the bulky base, tert-butoxide and tert-butanol. There are other big bases. But if you had to commit something to memory, that would be other bulky bases would be things like LDA. The thing about LDA is you need to use an aprotic solvent like THF or ether. Why? Because LDA is effectively N minus, right? If you put it in, say, methanol, all it is going to do is protonate your amine and generate methoxide. And then if you use this because you needed a big base and you use methoxide as or methanol as your solvent, you're just going to make a small base and it's going to do exactly the opposite reaction. So if you're using something, because this is effectively nitrogen bond to lithium, this bond is polarized in this direction, so it's effectively N minus. If you had tert-butyllithium, same thing, you would need to use THF or ether as your solvent because it would deprotonate a protic solvent. So if I need to use a bulky base, I'm typically the easiest one to commit to memory is tert-butoxide. Does that make sense? In fact, one year on one of the tests, I actually used, I did a question which was using LDA in the solvent in this. Yeah, I had to not include that question on the test because it wasn't, people missed it. So I probably won't be doing that in the future. But let's see here. So in the second question here, B, what would we be using? What type of reaction is going on here? So we're switching a tosylate for a cyano group or a nitrile. So this is a substitution reaction. What would be the next step in our analysis? So first step, we find out that it's a substitution reaction. Right, so we've determined that it is SN2 because we're on a secondary carbon and there is inversion. Right, so our tosylate's pointing towards us and now the nitrile is pointing away. So if it's a SN2 reaction, we need to come up with a aprotic solvent and you can use, there's a whole host of them that you can use. I think someone mentioned DMSO. You could use acetonitrile. DMF. Any of those would work. And what will our nucleophile be? Right. The cyano group. And it could be the sodium version or the potassium version, doesn't matter, but that's That's the nucleophile. And this is a good nucleophile because it's carbon with a negative charge. That's good. And also it's linear. So those are two things it's got going for us. And the other thing which is interesting is that it's not particularly basic, because remember when we were doing our, it's not like a normal carbon with a negative charge. This is an sp hybridized carbon. So it's stabilized by that type of orbital. And in addition, it's attached to a nitrogen, which helps with induction, stabilizing that with induction through electronegativity. Could we do a practice question to rank the best and worst nucleophile? Okay. Okay, so there's two questions here. For the solvents, all of these solvents are valid solvents. So if I put multiple solvents like this on a test, I would have to select the little star thing which says that any answer counts as being correct. So as long as they're aprotic, don't worry about, any one of them could be good. That would be, so there's different reasons why different solvents are, why you might choose them or not. And that, we sort of learn that later on. There's more practical implications for this. Okay, so just for the sake of knowing things, let's talk about some of the solvents here. So a lot of the reactions that people carry out in organic chemistry, which we don't really do in second year labs, often water is a big detriment to the reaction. Water can often cause issues. So a lot of the reactions that we do are under anhydrous or water, there's no water in it. DMF is a solvent which is polar and protic, but it's getting rid of water in it can be difficult. So it can be a pain. So DMF has got some practical pains to it. Acetonitrile, however, is really easy to use, and you can basically get it out of a bottle, and so that's helpful. The problem with acetonitrile is that later on next term, we're going to see that this part of the nitrile is reactive. So certain reactions you can't do it because what we're using is going to react with the nitrile. So that can be problematic. DMSO is probably, they call this the universal solvent because it's good at dissolving organic molecules and polar molecules and non-polar molecules. The trouble is that it goes through your skin. So if you're, it's a really strange sort of sensation. And I guess DMSO is sometimes used on farms. So if anyone's a farmer and you've used DMSO before, if you get it on your skin, you often get this weird taste in the back of your mouth. And that's basically, it's really strange because the moment it touches your skin, you actually can taste it. And the problem with that is that if you've dissolved something which is toxic, DMSO can bring it through your skin and poison you. So, and people have, died because they're working with something which is toxic. It's dissolved in DMSO and it gets through your skin and you bring it into your bloodstream and boom. So all three of these solvents have got little minor issues to them. THF is probably the most useful practical solvent because it's easy to dry, it's easy to get rid of the water, and it doesn't have any of these other side effects. So, but anyway, that's the little story about the solvents. But you can choose any of them really for what we're doing with the substitution reactions. Now, someone asked about Well, okay, let me just clear all this mess out. Okay, so we want to do there's been a request to do a ranking question. Best to worst for nucleophiles. I don't think that you actually need to remember the structure of the various, like THF is this one. We'll see that later on. Ether is this one. We'll see that a lot next term. DMSO is similar to acetone, which except for it's a sulfur. And DMF, I suppose, is the one which is a bit strange. I don't think you're never gonna need to know the structure of that in all honesty. So an acetonitrile it's just the simplest nitrile. It's just got a methyl group attached to it. So these are the ones which are, I think, important, which we'll see later on. I guess, but if you just write DMSO, that's fine. We don't really need quite to know the structure right away, so I'll just get rid of that. So let's do a ranking question for best to worst nucleophile. Okay, so how about this? Okay, so in this case here, I've done something slightly different. I've included the solvent. So under these conditions, which would be the best nucleophile, which would be second best, and which would be worst? So remember, the oxygen-based nucleophiles or negative charges can be both bases and nucleophiles. So this question is sort of, if you wanted something to behave as a nucleophile, which would be the best conditions for it? And what would be the worst? Actually, let's do one more too. No, let's leave this one out. Don't complicate things too much. So remember, so to be a good nucleophile, there's a couple of things if we're going to do an analysis of it, there are a couple of things to keep in mind. Okay, so there's structural things structural. I thought, and then there's also there's conditions as well. So in this case here, it's not really a structural question because in each case, it's an oxygen with a negative charge. So it's really the conditions that are in this case, playing the important role as to what would make something a better nucleophile or not. So is it, which of these conditions would promote the oxygen being a nucleophile? We have got, when it comes to voting, so far we have got 1 vote for B. And we've got 19 participants, so the voting record so far is very poor. EAC. Okay, so, right, okay, so, okay, good. So the under these conditions, the best the best conditions for being a nucleophile is in fact A. Okay, so remember, SN2 reactions are preferred in aprotic solvents. So in our little energy diagram over here, free energy reaction coordinate, if you've got a nucleophile, so this nucleophile, and it's in a protic solvent, okay, so this nucleophile's got a negative charge, it's going to be solvated by the solvent, by those hydroxyl, it's going to be hydrogen bonded to all of those little hydrogen atoms here. And so it's got all of the solvent surrounding it, and it stabilizes it. So I'll just put this energy here. If you're using a solvent which isn't great, it's solvating negative charges like DMSO, then it's going to start, the energy level is going to be higher. So it's going to start up here. Okay, so the next question is, how do we know if we're dealing with SN1 or SN2? Okay, we'll deal with that in a second. Okay, so the energy level in an aprotic solvent is going to be higher. So this activation energy, this delta G dagger, is going to be smaller. So if methoxide is going to be your nucleophile, the best conditions would be in an aprotic solvent. So A should be the best nucleophile. And I did B or C for the second reason, and this is the structural part of this here. So oxygen's attacking, and remember, what do nucleophiles attack? They attack nuclei, so carbon. And I purposely made this one over here, this isopropyl. What does this have, which is bad, that this doesn't have? C has got something which is detrimental, steric hindrance, right? So C is sterically hindered. And whenever you're attacking, and like to attack a nucleus is a lot different than grabbing a proton. Protons are small, they're easy, they're more on the periphery, so they're easier to pick off, so to speak. Whereas if you want to attack a nucleus, you really got, there's a lot more, like sterics plays a much larger role. So the order for best to worst nucleophile in this case would be the best would be A, then followed by B, and then followed by C. And so, yeah, this would be the order, because C has got steric issues, and the difference between A and B is that the solvent is going to promote this behaving as a nucleophile, whereas over here, this is going to make behaving as a nucleophile harder, and it's going to promote elimination reaction. So the question about how do we know if we're dealing with SN1 or SN2? The problem with oxygen-based nucleophiles like methoxide, these can be strong bases. So you can't use methoxide in an SN1 reaction because you're going to do an elimination reaction. You can use it in an SN2, but you're always running the risk of an E2 being a side product of that. So on our little decision matrix, let me clear this. Like, using methoxide as a nucleophile is always going to be a little bit touchy. Oxygen-based nucleophiles that are stabilized by resonance, or the phenoxide one here. On our little decision matrix thing, we said these aren't strong bases because they're stabilized by resonance. And they're not strong, but they tend to behave as nucleophiles better than they behave as bases because there is this resonance stabilization. So methoxide is always a real tricky one if you want to use it as a nucleophile because it runs the risk of E2 eliminations. Okay, well, let's do a different example without oxygen. Clear that. Okay, rank the following as nucleophiles. Mm-hmm. Oops. Actually, let's get rid of this one here. So in many ways, nucleophilicity, if we're dealing with charged, the nucleophilicity basically is increasing as polarizability increases. And remember, that increases as you're going down the periodic table. So sulfur is more polarizable than oxygen. Iodine is more polarizable than bromine, which is more polarizable than chlorine. So if you're comparing sulfur to oxygen, anything with a negative charge is typically a better nucleophile than something without a negative charge. So SH minus is going to be better than SH2. And then sulfur is going to be a better nucleophile than oxygen because it's lower on the periodic table. So this would be better than, say, water. And if we did the halogens, iodide would be a better nucleophile than bromide versus chloride versus fluoride. Now there is some sort of there is some reversal of this depending upon like certain conditions with regard to the solvent, but for what we're dealing with, it's really iodide is better than bromide, which is better than chloride. Iodide is a pretty good nucleophile. It's not a base. Bromide's not a bad nucleophile. It's not a base. When you get to fluoride, though, fluoride can be a base. So we don't. It's one of the. So this trend on the periodic table, as you get lower, as the negative charges get stabilized in a larger atomic orbital, these species aren't bases at all, right? They are, like from a Bronsted-Lowry perspective, they're not bases at all, but they can be really, really good nucleophiles. So if there's a question like this, just remember this trend or a trend like this as well. As you get lower on the periodic table, the nucleophilicity seems to increase. Selenium is right underneath sulfur, and selenium would be a better nucleophile than sulfur. Selenium just happens to stink to high heaven, so it's worse than sulfur when it comes to stench, so it's not used as much. Yeah, if you want, I can post this to on Top Hat if you like. It's a bit scattered, I guess. Were there any other questions? Okay, let's see here. Well, if you're leaving to write a test, good luck on your tests. And we still have another review on Sunday evening as well, yes.
Dr. Hill.
Yes.
I didn't get it down. In the first question we did about ranking the nucleophiles, did we decide which one was SN1 and SN2?
Okay, just in this last little part?
Just the question before it. I'm sorry, I forgot to ask right before we moved on.
Okay, so yeah, if we're asking, let me see here. So yeah, if in the previous for this DMSO versus OME in methanol. Okay, so DMSO, this would be for an SN2 reaction, whereas this, if you're using methanol, this would, you could do this in an SN1, right? But the trouble is that for an SN1 reaction, the rates basically, it doesn't involve, it's just the Rx. It doesn't involve the nucleophile at all. So if we were to try to use methoxide in methanol for an SN1 reaction, we wouldn't get an SN1 reaction at all. We would get an E2 elimination. So this would behave as a base. So when we're asking about substitution, like what's the better nucleophile, the way that this has always been tested is let's erase this for a second. Like, I think the example we gave in class was that the experiment which would do this would be a methyl alkyl halide. X could be bromide or whatever it might be. And the nucleophile would be based upon this because you're eliminating the possibility of an elimination reaction from taking place, because there's no, remember, to do an elimination reaction, you need a carbon next door here which has a proton. And in the case of a methyl group, there is no, elimination reactions are impossible. And so in these instances, if you've got a protic solvent, the activation energy is higher compared to having an aprotic solvent, but the actual reaction itself is a SN2 reaction. So you don't compare, like for an SN1 reaction, because the nucleophile isn't in the rate determining step, it's not important. It's just it's the alkyl halide which is the important thing for the rate of a SN1. So whenever there's a question asked, what's the better nucleophile, we have to make the assumption that it's a SN2 reaction which is taking place. Does that make sense?
Yes, it does. Thank you.
Okay. Okay, so I've got a question here about energy diagrams when there's 3 bumps instead of 2. And I think I know an example of what this might be. Okay, so let's erase this. Okay, so you guys did this reaction in class. Oh no, not yet. Forgetting that we don't have a lab yet this year. Okay. And this was done in so you guys did this reaction, or did you guys do this reaction this term online? So this is a SN1 reaction. So and the way that this works is that, so hydroxide's not a leaving group, right? We need to make it into a leaving group. And the leaving group we're going to make it into is water. Then it needs to leave to form a carbocation. And then the chloride needs to attack to form your final product. So if we're going to draw all the arrows of how this mechanism works, the first step is an acid-base reaction. Lewis, here is our base, here's our acid, leaving group leaves, and we form this intermediate here, which we'll call A. Then next step is the leaving group departs, and we form B. And we still have our chloride hanging around from the first step, and it attacks the carbocation, and it gives us our final product C. And so this, if we drew an energy diagram of this, you will notice that there's actually two intermediates. There's intermediate A and there's intermediate B. And so on your energy diagram, it might look something like you form one product, you form another product, and then you form your final product. So this might be A, intermediate A. This would be intermediate B. And then C, your final product would be down here. So the first part is just protonation of that alcohol. And then this step, I might have drawn that thing a little bit too high. This is reversible because it could just lose the proton to water. And then the main part, the rate determining step would be the formation of the carbocation. And then the last bit would be really quick, formation of C. Where most of the examples we've seen before for an SN1 reaction is just, we've got some group which is a good leaving group right at the start, and it just departs. And so the energy diagram for that's just, you know, the carbocation, it's just that one step. So this is an example I can think of in which there are like a couple of stages to it. And I think that's the one I can think of off the top of my head. Does that make sense to the person who asked the question? And so there's a couple of practical things in this question here. You notice that the solvent's water and diethyl ether. This is about solubility. So it's like almost an equal mixture of the two to make this work. Yeah, this is a fun little reaction when you get to do it. But yeah, so that's an example of an energy diagram which has got a couple of bumps. The first one is just protonating it to make a good, because you need a good, this is now a good leaving group. Good leaving group. But the high energy intermediate will still be B, because that's the carbon with the positive charge. Are there any other questions at all? Okay, well, what we can do if there aren't any, we'll still be doing, we'll do another review on Sunday evening at 8. Try the practice Moodle questions and try the practice questions on the test. posted the answers to the last midterm online, so you can take a look at those. But yeah, just give all of those things a crack. And I'll see everybody on Sunday at the earliest and Monday at the latest, I suppose. All right?
Thank you.
Heck, you bet.
Thank you.